Hello, my name is Abdulmajid Karanouh, and I'm a lead consultant at Aedas Architects and part of the research and development group. I'm specialized in design innovation and delivery. My background is in architecture, computing and design, and facade engineering. There's a lot of interesting things that my colleague presenters just showed us. I am not going to be necessarily talking about design algorithms as such, or let's just say new architectural trends. I am going to be focusing on whatever it is, the algorithms or the designs that we come up with. How are we actually going to communicate this data and channel it down to the wider supply chain and perhaps maybe to the lower level of skills and labor who are actually going to build our buildings. So in that respect, we are not alone on the project. We do have lots of people who are going to be working with us, and they may not necessarily understand the language that we're using or the tools that we're trying to develop. We have developed a lot of tools in order to deal with complexity, and obviously this is a Gary project in Switzerland, and credit to Gary Technologies. So lots of things to do with computation, parametric design, BIM, and so on. However, recently, things are developing more than just complex geometries. They are developing into more interactive, responsive, adaptive type of solutions and systems, whether they're digital or whether they're actually mechanized or mechanical. So there's this fourth dimension now that is being introduced, and obviously that is increasing complexity, and accordingly it is increasing the data. So therefore, how do we communicate? How do we communicate design and construction intent, a performance criteria, rules? In terms of design and construction intent, there are the traditional or the common means by doing sketching, 2D drawings, 3D models, physical models, BIM, and so on. However, there is an issue that always lies within doing things like BIM, for instance, and that is ownership. Who owns the model? Who is in control of the model? Can we actually hand in all the components of the building that are being developed and designed by different parties, different disciplines, different contractors, to only one party to control? Some people may accept that, but many people will find this a bit inconvenient to them, and they will resist it. And it's something that I have learned the hard way on the project that I'm going to be presenting you in a while. But then again, as we said, you may be able to finally do that in terms of complexity, in terms of geometric complexity. But then when it comes to performance criteria, how can you then deliver or convey or communicate a performance criteria which is not necessarily geometric? And then you may say, well, we can use building codes and standards. But then what if you face a bespoke solution where building codes and standards don't cover? Then what do? You say, well, fine, we can come up with our own rules. We can do our algorithms, parametric and computational design and analysis and so on. Excellent, very nice. But then how do you communicate down to the lower supply chain? In what language, in what format? If you're just going to give them an algorithm, a written algorithm, or a written code, that may not do the job. You would need something a bit different. So the case study that I'm going to be presenting is the Al Bahar Towers. These are 2 office buildings. It's an invited competition that we won back in 2007 for the Abu Dhabi Investment Council in Abu Dhabi, United Arab Emirates, in collaboration with Arab. For us, really, the concept was very simple, and it was in response to the design brief, and that is the client wanted an international landmark which is related to the local heritage and environment. So really, we tried to look at the local environment, we tried to look at the local heritage in terms of the architectural styles, perhaps, and then try to find suitable technologies to respond in a contemporary manner. The building won Best Innovation Award 2012, offered by the Council for Tall Building and Urban Habitat. And as you can see here, the north face of the building does not have this sort of veil or shading screen. That is because there's no direct sunlight coming there. But then again, from east all the way to west, what do we do when you have intense sun in a sunny area like Abu Dhabi? We did a lot of studies to optimize the form in order to make it more aerodynamic, more fluid, to try to maximize the volume, minimize the surface area so that it becomes more energy efficient. We also we came up with this nice honeycomb structure, which is very robust, quite efficient. But then the focus that I'm going to be presenting today is really this dynamic shading screen. You can either have a static building, which pretty much you can use an analogy as a static or a dead flower, which doesn't change throughout the day or the season. But then again, this is what makes nature efficient and beautiful, is the fact that it does interact and it does respond to the changing environment. So we use this very simple concept by deriving from inspiration from past features like the Mashrabiyah, which is a solar screen, a geometric solar screen. But we try to insert this fourth dimension into it and see how it can fold and unfold following the movement of the sun. So for instance, when the sun is there, then the whole thing will unfold like an umbrella. But then when the sun moves away, it starts folding. I'm going to show you here quickly a video that will explain the story in a bit more eloquent and nicely produced way. It's a combination of a CNN video and a, so I don't think the audio is working. Okay.
When architect Abdulmajid Karanouh was asked to design twin buildings in Abu Dhabi that are contemporary, sustainable, and culturally relevant, he looked to tradition.
Not allowing the sun to land directly on the skin of the building, causing overheating and glare, was a very simple concept. And that's why using the Mashrabiyah, inspired from the past and inspired from nature, was a no-brainer.
The north side of the buildings, which never receive direct sunlight, are unshaded. The architectural challenge was how to build a facade that could mirror the dynamic movement of the sun.
So we started looking at something that could be more three-dimensional, offer more flexibility, offer more geometrical shapes that could adjust to the movement of the sun.
The Mashrabiyah. The idea is to use a geometric pattern to produce shade. The early designs lived up to the old ways.
It occurred to us that in order to be truly effective in a modern-day idiom, the sun moves around the building in a dynamic fashion, and the facade needed to be capable of responding to the movement of the sun in a similar way.
Senior designer Abdulmajid took on the challenge. His solution? Origami.
We took the triangle, we subdivided it into 6 triangles, and then we fold 3 sides inwards, and we folded the three opposing sides outwards. Instantly, it was, Peter was like, "That's it, this is it. We want to do it."
It was the moment when we realized, I think, that we had something special.
The first animations led to ones more sophisticated. They show computerized umbrellas responding to the sun. Here's the view from inside.
We do have the data telling us what the behavior of the sun and the trajectory or the path of the sun is going to be throughout the day and throughout the year.
So 1,000 umbrellas are programmed to automatically open to block the sun, and they close when it is passed.
So if it's early in the morning, let's say, and the sun is low, you will have a complete open strip all the way from the top to the bottom. Now, as the sun starts moving around, the ones that were completely unfold will start folding gradually, while the ones were now facing the sun, they will unfold completely.
They put up a small section of the system to test it on site. This view from the inside shows that the Mashrabiyah is 2 meters from the building. That's far enough for the mesh to block the sun, but let in light.
The Mashrabiyah provides about 80% shading.
So you get a view with benefits. One of the first pluses is in the choice of windows. They don't have to be heavily tinted.
So you can have better light transmission up to 40% as compared to other buildings in UAE where it's down to 15%, 10%, and some of them even as low as 5%. So ironically, in one of the sunniest and brightest areas of the world, you actually have a poor lit environment. So you have to use the artificial lighting for most of the time.
Not so with the Mashrabiyah. And it also means they'll use less air conditioning.
It'll use less energy, so it'll produce less carbon, so it'll respond to all of the challenge which all of us face in this modern age.
Each unit is made of 30 components. The frame is a combination of aluminum and duplex stainless steel.
It has a high resistance to corrosion. This building is facing the sea, so it's a fairly aggressive environment.
The mesh is fiberglass.
But fiberglass alone is not durable enough, so we had to sort of coat it with PTFE, which is a Teflon-based material.
The struts holding the units are stout, weighing 240 kilograms. They have to be. Some units are 6 meters by 4 and weigh more than 600 kilos.
Making sure that this system is structurally robust enough and mechanically reliable enough in order to last for the lifetime of the building. We had to do rigorous testing for the system.
That testing was done in Switzerland. They brought sand, dust, and salt water from Abu Dhabi. They sprayed that mixture on the Mashrabiyah and then cranked up the heat to 60 degrees Celsius. They ran it for 30,000 cycles, the equivalent of 75 years. Next, it faced a wind tunnel in France and its many sensors.
And we put it at the worst condition that we think it's going to be subject to, and that is when the wind is trying to blow parallel to the Mashrabiyah. Because when it's parallel to the Mashrabiyah, it provides the maximum suction effect.
A wind speed of 240 kilometers an hour barely moved it.
We have anticipated roughly up to 50 millimeters, but when we did the wind tunnel, the deflections really did not exceed 25 to 30 millimeters. Right, sorry, I had to edit the video. This is the algorithm that runs the solar panels following the movement of the sun. Now, obviously, we cannot go to the client and say, that's how the facade is going to work, or even the subcontractors for that matter. So we needed to find a different way to present the whole thing. Add to the fact that it's not just the performance, there's also not just the performance and the geometry, there's also all these mechanical components associated to each unit. And the fact that because we have this sort of organic looking building, these will come in various sizes. So we needed to make sure that whatever mechanism that we develop, that we're not going to end up engineering each and every single piece differently. So for instance, we needed to develop a universal solution that can adapt to the different sizes and the different locations. So what you see here is the building that will have all different kinds of sensors from light and wind that will detect unusual conditions, and then will order the Mashrabiyahs to fold and unfold accordingly. We've done all kinds of optimization for the panels, the geometry, the flatness, and so on. And you can see there, not only that we've graphically represented, say for instance, how much each panel is twisting, but we've also digitally printed on each panel how much it is deviated, how much is it flat, so that the contractors can take it and can read it, can interact with it visually, and take the data numerically. But then there's the integration of all the different elements of the building. There's the form, there's the structure, the envelope, and then there's this adaptive shading screen on the outside. So we needed to find a way, not just to integrate these together, but then again, how we're going to communicate the data down. And this is where we started thinking of something like the DNA. Now, we've borrowed some ideas from the automotive and the aerospace industry, where you just literally just create a catalog and you show, like Lego, for instance, how the whole building is constructed piece by piece, and then how it develops accordingly. And so what we've done is we've developed this 280 pages manual that shows the construction starting from the grid all the way up to the performance of the Mashrabiyah and how it actually moves. So basically, we have illustrated our words to make it, our rules to make it short. And then we script these rules just as a proof of concept. And basically what you're going to see here is all the different components of the building, because of the Islamic geometry, basically derived from circles and spheres. All of the geometry that you're going to see here is also derived of or constructed from circles and spheres. And then we produce these diagrams that will identify the finishes, for instance, the main structure, the facade, the external shading screen, and we give these guidelines to all of the different subcontractors, and we give them this manual that you're going to show just a few glimpses of it. So this is a quick run of the manual. And basically what this manual does really, it liberates us from having to force the process down to a certain tool or a certain package. We don't have to use, say, for example, Digital Project or Grasshopper and say, all of you have to use exactly the same tool. Because facade contractors, for example, they wanted to use Inventor. The steel contractors, they want to use Tekla. Ultimately, we ended up using 13 different packages, not internally, but throughout the whole project team. And it was this document that liberated us from using one package. So everyone can use their own packages and develop their own scopes to their own tolerances. As long as they're following the same mathematical rules and the same instructions, they will end up with the same geometry that doesn't clash with the other scopes. And then finally, when each of the subcontractors or the contractors develop their own scope and their own items, then we bring them in together into the Digital Project, which GR Technologies assisted us in doing so, and just make sure that there are no clashes. And it's really very easy. If we find only one or two components, we know that they haven't followed our mathematical rules. So we don't have to carry a thorough check through all the thousands of different components. So ultimately, we develop the wireframe using our rules. We give them to, let's say here, the steel contractors. They develop the structure digitally, and then you see the whole thing being realized. These are, for instance, some of the data that we've extracted out of the algorithm. And you can see that communicating in this manner now becomes a lot easier because we're not anymore relying on numericals. What you see here is every one of these strips is actually a floor plate. So you have a strip of mashrabiyas, and these are the ones that are going to be unfold. The one which is highlighted in the middle is going to be midfold, and then the one over there is going to be completely folded. And you see here the times of the day over there. So this starts early in the morning, and then it goes through noontime all the way to the afternoon. So it becomes something more representable, something which can be legible, and people can better understand it. But then again, there are issues related to quality. How can you, for instance, quantify something which is perceived differently from person to person and region to region, which is glare? People in the Middle East, for instance, they might find glare or perceive glare differently to people in Northern Europe. And as a multinational company, they're going to have employees from all over the world. So it was important to do physical one-to-one prototypes and be able to test these prototypes. And again, you've seen in the videos things like the sand, for instance, and the salt and so on. There's only so much you can do in order to digitally simulate these things. Ultimately, you've got to build these up and you've got to test them. So to close the presentation here, you see, for instance, the different installation methods. We measure before installation, during installation, and after installation to make sure that everything is not deflecting over the allowed tolerance. Our supply chain spanned from Minneapolis, US, all the way to Osaka, Japan. So really, in effect, there's a lot of interrelated things related to design innovation, the context, the science, the design team, and obviously construction. But what I specifically tried to focus on for the purpose of this project was the interrelationship between architecture, engineering and construction, computation, and mathematics. And really, you will find that the core of architecture is all about multifunctionality. The core of mathematics is about algorithmic design. The core of computation is about process automation, automating the process. And the core of engineering and construction is about systems design and delivering technologies which will fulfill the required performance criteria. So in a nutshell, we start from really simple means like doing some little physical models or sketches, and then we go into far more advanced digital simulation. And then we develop, this is the critical part where we develop the DNA of the building. And then we integrate it into BIM, and then give it back to the manufacturers, who then will test it, mass produce it, and finally install it. So, and that's this is the building now. We're still working on optimizing the opening and closing of the units. And this is the view from inside, and you can see the visibility is quite clear. So the last point is well, the answer basically is how do we communicate design and construction intent, performance criteria, and design rules? A simple suggestion would be really, we need to develop integrated universal design solutions, things that can self-adjust to the different cases without having to engineer each and every single component for every single case. And then we need to be able to illustrate the rules where people that do not have the same background that we do to understand them. And then finally, no matter how confident we are with what we have seen and what we have simulated, it's very important to build prototypes and test them, because the most unpleasant surprises lie where you least expect them, really. And thank you.